Welcome to Chapter 20. Chapter 20 covers carboxylic acids and their derivatives. And I must tell you, this chapter is large and in charge. And so it's going to take some staying organized and, pacing yourself to get through this chapter and feel good about it. So let's jump into the first section about carboxylic acids. All right, we should all recognize the carboxylic acid functional group. Right, it was a carbonyl with an OH. Now, on the other side, you could have the smallest carboxylic acid would have a hydrogen, or you could have any R group here. All right, as Klein loves to do, here is a random assortment of carboxylic acids, everything from acetic to butanoic, hexanoic. As you get longer and more substituted, there's a lot of common names involved. Something that you might have noticed from the carboxylic acid lab, even though you didn't get to smell the carboxylic acids, you definitely heard about them. Acetic acid, responsible for the pungent smell of vinegar. Butanoic acid, rancid or sour butter. Also smells a lot like vomit. Hexanoic acid, the odor of dirty socks. Right? Lactic acid, sour milk. They're not known for smelling great. This functional group is present in many other compounds as well. Some that don't smell like anything, some that probably smell good. But they are known for being kind of stinky. Now, when it comes to small carboxylic acids like acetic acid, this is an important compound in industry. Right? You see here that the U.S. produces over 2.5 million tons per year. It is an important starting material for a number of different products, including vinyl acetate, right? Used in paints and adhesives. It's very common, these reactions where you see like a rhodium catalyst or really high pressures or temperatures. It's interesting if you're in chemical engineering, that's something that you'll study more in your future. But for organic, we stick to the more small small organic reactions. And we don't look so much at big industry. Now, naming. You're going to have two big sets of nomenclature in this chapter, and I should say you're going to have two sets of nomenclature. One that's small, where we study carboxylic acids, and then in a few sections, you're going to have a much larger one where we study all of the derivatives. So you are going to need to practice with your nomenclature. All right, so the carboxylic acid nomenclature. This is the highest priority functional group that you are going to learn. So if a carboxylic acid is present, it will be the parent, right? The longest chain with the carboxylic acid will be the parent. What you want to do is you always want to start at the carboxylic acid end. All right, so let's see. You have for instance, this example over here, it's a 4-carbon chain. So butane, right? You take just the E. You leave the AN and you drop the E. And you're going to add ic acid. Okay, so butane becomes oic acid. Becomes butanoic acid. Right, not butoic acid, butanoic acid. So you want to keep that AN. Everything else is, these rules. So if we look at this more complicated structure, we want the longest chain, 1, 2, 3, 4, 5, that contains both the carboxylic acid and then the most number of substituents. So you could also number down this way, but then you would have a complex substituent here. Since it's 5 carbons long, pentane becomes pentanoic acid. Right? You should know how to name an alcohol if it's not the high priority. It's a hydroxy group. You have your 2 methyls on 4, but then you write them down alphabetically. H comes before M, right? Di doesn't count. Anything that's just telling you a number doesn't count alphabetically, but H in hydroxy comes before M in methyl. And that's how you get 5-hydroxy, 4,4-dimethyl pentanoic acid. Before we move on from that, I do want to address, you could see an alkene, right? If we had an alkene, you're still just going to drop the E and add oic acid. So let's say we had something like this guy. Put a fluorine in there. Why not? OH. All right, now in this scenario, we have 1, 2, 3, 4, 5, 6. So this is a hexanoic acid, but it has an alkene in it. So it's from hexene, not hexane. So this is a hexenoic acid. We do need to say where the double bond is. It's at carbon 3. It's a hexene oic acid. You don't ever have to say where the oic acid is because it's always going to be on carbon 1. Now, something that you should note here is there is stereochemistry involved here. If we look at this particular double bond, right, there's an H coming up here, right? We cut down the center. Fluorine beats carbon. Carbon beats hydrogen. The ones are on the same side, and so this is a Z stereoisomer. Right, so we're going to put Z out here in front. This is a Z 4-fluoro hex 3-enoic acid. You still have to know your stereochemistry. E and Z, R and S. It won't make or break you, but it will be necessary if you want all the points on an exam. Now, I don't care for you to know the carboxylic acid on a cyclohexane up here. I will be skipping that. But there are a few common names that you need to know. Right? Common names like formic and acetic acid. I do want you to know to the point where I'm going to repeat them, even though they're on the slide right next to me. Right? This would be methanoic acid. But you should know its common name of formic acid. Ethanoic acid. You must know that this is acetic acid, right? Ethanoic would be IUPAC. Acetic would be common, but I have never found a bottle of ethanoic acid. There's always a label that says acetic acid. Now, propionic and butyric, I'm not going to require you to know that, but you will see those frequently. Those are close, right? Propionic versus propanoic, butyric versus butanoic, that you can often figure them out. But these two I want you to memorize. Benzoic acid you've already had to memorize. And so you should still know that one. If you have a dicarboxylic acid, you are going to, right, so you're going to have 2 carboxylic acids on the same parent, right? You're going to want to choose the parent that has both the carboxylic acids. You are going to still count 1, 2, 3, 4, 5, and you're not going to drop anything, right? You are going to leave alkane and add dioic acid. You don't have to say where they are because they're going to be on the ends, right? And then you're going to, if you have to number, well, we'll do an example with that in a moment. This right here is a pretty simple one, pentane dioic acid. Actually, let's do that example here. Let's pick off of the top of my head, dioic acid here. And then let's put a couple of different things in here. All right, we have a few functional groups. Carboxylic acids are highest priority, so that gives us the parent. Now, I could number from the left or the right, and I'm going to have my carboxylic acids on the end. So I'm going to number to give the lowest locants possible to the tiebreakers here. 6, 7, 8. So I have an octane dioic acid. I have a hydroxy group on 4. So it's 4-hydroxy. And I have an oxo on 3. And then octane dioic acid. There are a couple of common names that you need to know, and it's just going to be these first two. Instead of ethane dioic acid, you should know oxalic acid. And instead of propane dioic, you have malonic acid. I may ask you about these. Malonic acid will definitely come up in the next chapter. So I do want you to know these common names. Carboxylic acids have a lot of very widely used common names. So I'm not going to ask you to memorize all of them. But formic, acetic, oxalic, and malonic, you should know. I will test you on some of those. Okay, practice your nomenclature. Now, structure and properties of carboxylic acids, we've covered from time to time, and it shouldn't be too surprising. They have a trigonal planar geometry, right? You have that sp2 carbon at that carbonyl. It's acidic. It's capable of very strong hydrogen bonding because each functional group can form 2 different hydrogen bonds. This is going to, unsurprisingly, result in higher boiling points. All right, so carboxylic acids tend to have higher boiling points than similarly sized alcohols. They're also called acids because they are acidic. It is not that hard to pull a proton off of your carboxylic acid. In fact, it's a lot easier than even an alcohol. All right, now sometimes I'm not going to ask you to name these, but when a carboxylic acid has been deprotonated, it is called a carboxylate. So sometimes you will see that O8 when talking about these salts. Now that can get a little confusing later with ester nomenclature, so I'm not going to ask you to name these. But when you're reading things in labs or journal articles, it's important to recognize that the deprotonated carboxylic acid gets that ATE ending. Now, choosing the appropriate base to deprotonate is important. We know that these carboxylic acids are actually weak acids, meaning that they do dissociate in water. It's just most of them will be in their neutral form, right? The equilibrium arrow lies towards the starting materials. Now, what's attached to the carboxylic acid can affect the pKa. We've studied that already. I'm not going to ask you about, to predict pKa's here or predict ordering of strengths of acids. What you should know, though, it is considerably more acidic than an alcohol. And when you remove that hydrogen, in both cases, you get a negative charge on the oxygen. But what makes this so much more acidic is that resonance. If you took the hydrogen off of ethanol, you wind up with this guy. And that negative charge on that oxygen is just stuck there, right? Whereas on the carboxylic acid, it spreads out. Both oxygens share that burden, right? So this is a lot more stable. And if it's more stable, that means it's a weak conjugate base. A weaker conjugate base means that we have a stronger acid in comparison to the water. I will not ask you to calculate pHs, pKa's, or deal with Henderson-Hasselbalch. But what is good to know about carboxylic acids is they have a lot of uses in chemistry. They can be used as a buffer. We won't be getting into that here. When you get into biochemistry, the pH issues, physiological pH of of different reactions of systems that have carboxylic acids can be really important. If you want that proton to be on your carboxylic acid or you want it to be removed, pH is extremely important. These trends here in pKa's is nothing new. When we talked about REO in chapter 3 of Organic 1, we discussed how electron withdrawing groups can affect acidity through the inductive effect. Again, will not be asking you to rank these for me, but you might see it in your homework. It's more just about prediction. Now, where we're going to wrap up here is just a very quick review of preparation of carboxylic acids. Several of these reactions are old Organic 1 or just from earlier in the semester. You have, let's start on a new page here. You have ways to make carboxylic acids already in your toolbox. If you have an alkyne, and not a terminal alkyne, well, it has to have at least one R group on it. You treat it with ozone, and then if you remember, ozonolysis of alkynes only needs a water workup. You are going to cut that triple bond in half, and you are going to oxidize, right? Every bond here, 1, 2, 3, that was to carbon is now to oxygen, right? And so let's say you had 2 different R groups, then you would make 2 different carboxylic acids. That's review 1. There's oxidation reactions with primary alcohols, right? If you have a primary alcohol and you treat it with Jones reagent or sodium dichromate and acid, you could also use KMNO4. You can oxidize this all the way up to a carboxylic acid. Remember, PCC would stop you at an aldehyde. A strong chrome reagent is going to take you all the way to that carboxylic acid. You also learned about oxidizing the benzylic position in our previous unit. So as long as there's a hydrogen on that benzylic position, right, using those strong oxidizing reagents like we did in the last section will give you a benzoic acid or a benzoic acid derivative. All right, that one's really new. You should definitely still have that one. A couple of new ways that you could prepare, and you're going to learn a few in this chapter, but up front, it's hydrolysis. You can hydrolyze most carboxylic acid derivatives, and so I'm going to focus on those as we talk about each derivative instead of talking about one random one up here. But if you take any of these derivatives and you treat with H3O plus, right, acid catalyst and a lot of water, you will get a carboxylic acid back. We'll look at this in more detail when we get to nitriles. One last way that I want to leave you with here is preparation of a carboxylic acid using a Grignard. This can be really helpful, especially when you're dealing with kind of an sp2 carbon. It's kind of hard to work with. If you take any Grignard, right, so RMGBR, and you react it with CO2 and then do your workup with H2O, you are going to add a carboxylic acid onto that R group. Oh my goodness. Hello, come back. There we go. Onto that R group. This can be really useful. Now you see in this example, they use H3O plus, H2O, H3O plus, whichever you put in that second part. It's there to protonate. Since it's a carboxylic acid, it might make sense to decrease that pH some, just to make sure it's protonated. It's a really simple mechanism. I'm not going to ask you for the mechanism, but you're just attacking that carbonyl like you always do with a Grignard, and then it moves one bond right? We can't have 5 bonds on carbon. So one moves out to one of those oxygens, and then you just have to protonate it. This could be really useful for, say, adding a carboxylic acid on directly to a ring, right? If you were having difficulties, you couldn't use Frito Crafts for whatever reason, you could react that with magnesium. You make the Grignard, MgBr. You react it with CO2 and an acid workup, and voila. Another way to get to a benzoic acid. All right, this is really a nice little tool for synthesis. So make sure you add this to reactions that you should know. It's a Grignard, but it's just a slight modification. We haven't done it with with carbon dioxide before. And that's just what I wrote down over here. Now, you will see ether here. That's the solvent. You just want to make sure you have an aprotic solvent. Ether is really unreactive, and it's a very common solvent for Grignards. If you write it, if you don't write it, it's fine. ET2O is the same thing as this over here. I'm not concerned if you write the